Hello, this is Ernest Macalalad, and we're going to talk about gravitation. Gravitational force or gravity is one of the four fundamental forces in nature, and this arises from the masses between two interacting particles. In 1687, Sir Isaac Newton, in his work Principia, formulated the law of universal gravitation. So, for example, we have two particles, and let's say these two particles have masses m1 and m2. Okay, so the law of universal gravitation, as stated by Sir Isaac Newton, states that every particle in the universe attracts every other particle with a force whose magnitude is proportional to the product of the masses of the two particles. In this case, m1 and m2. And it is also inversely proportional to the square of the distance between them. So in this case, that's r squared, wherein r is the distance between m1 and m2. Okay? Also, because force is a magnitude, the direction of the force lies along the straight line connecting the two particles, and it is always attractive. Okay? So if we're going to draw or rewrite this expression in equation form can be written as F equals negative G m1 m2 over r squared. Okay, and what is the direction? Okay, so if we're going to define the direction as follows, so let's define a unit vector r12 this way. So this is r12 hat. Okay, so this unit vector is the unit vector with respect to m1, and it points towards m2. This unit vector is along this line. Okay, so this equation or this function of force, or this force, becomes a vector. Let's call this vector f12, and the unit vector would be r12 hat. Okay, so if we're going to draw this vector, we're going to express this as this one. This is f12. Okay, so you will notice that this equation follows an inverse square law, wherein the magnitude varies directly with a square of its distance. Again, so F12 is now the force exerted on particle 1 with mass m1 by particle 2 of mass m2. Okay? Also, this proportionality constant G can now be expressed in terms of constant. We call this G the universal constant of gravitation. And this is numerically equal to 6.673 times 10 to the negative 11. Okay, and the unit, because this is a quantity of force, so the resulting unit of this mathematical manipulation should be newtons. So mass and mass, so this will be kilogram squared, and this is r squared, so this is in meters, so this should be in Newton meter squared per kilogram squared. Okay, so by Newton's third law, this equation, so by Newton's third law, okay, F1 2 is equal to negative F2 1. So in this case, negative F2 1 will be this force. Okay, so as you will notice that this force, F12 and F21, lie along the same line. That line is the line that connects the two particles that are interacting. Okay, and these kinds of forces are called central forces because they follow the third law of motion in its strong form. Okay, again, central forces are forces whose lines of action either emanate or terminate on a single point or a center. Also, you will notice that the force on a particle is isotropic. So what does it mean? Okay, so imagine we have a particle of a certain mass. Let's call it mass m. And we want to find the force exerted on a particle, for example, on you, at a surface on a sphere wherein m is the center. So for example, if this is the spherical surface, okay, if this is the spherical surface of the that I'm talking about, and let's say you are positioned here, here, or let's say here. Okay, the magnitude of the gravitational force, okay, will always be directed towards the center. Let's call this F1. Let's call this F2. Let's call this F3. And because the particle, the source of the gravitational force exerted on you, okay, are all equidistant from your three locations, we know that the magnitude of the forces F1, F2, and F3 are all equal. So that means the force of attraction will always be directed to the center, and by knowing this force, you can never know the position wherein you are located. In other words, nothing about this force can be used to determine the location or your position within the surface. So therefore, this is known as the isotropic property of gravity. Okay. Now, that force is the force exerted by a particle with another particle. So what if we have a force, you want to know the force on a point mass due to a continuous charge distribution. Due to a continuous mass distribution. Okay, so if we're going to set up our coordinate axis, let's call this x, y, and z. And let's say we have a continuous mass distribution like this. Okay, and this continuous mass distribution can be expressed by this volume element dv prime. And this dv prime is defined by its position vector r prime. Okay. Now let's place our mass, our point mass, somewhere here. Okay, the mass of that particle, let's say, is m. Okay, so this m can be defined by two position vectors. The first position vector can be defined as the position vector with respect to the volume element. Let's call this script r. And we could also define this vector in terms of the origin. That origin and the vector is drawn like this. So let's call this r. Okay, taking note that r vector is equal to r minus r prime. Okay. Also, we can also define the unit vector r hat, script r hat. Okay, so where script r hat is equal to the quotient or the ratio between the vector r, script r, to the distance between the volume element and your mass. Okay, so if for two particles, okay, for the two particles we have m1 m2 over r squared times negative g r12 hat. For this configuration, the gravitational force can now be rewritten as negative g times our point mass m times the integral of rho r prime divided by script r squared dv prime r hat. So you will notice that this equation tells us that we are going to sum all the contributions of all the elements within this volume to the gravitational force exerted on our mass. Okay. Also, we must take note that the origin is arbitrary. So sometimes we're going to put our origin within the volume depending on the situation that we're going to have. So again, our script r hat is the unit vector that points from your volume element dv prime to m. Also, our rho is what we call your mass density. And here we assume that the mass density varies with position. So that means at any given point, in this case, it's possible that the density is not the same. Okay? And then dV, as I mentioned earlier, is the volume element defined by the position r prime. Okay? And this volume element is within the mass distribution. Okay? So that ends this short lecture. In the next lecture, we're going to talk about gravitational potential. Okay, for now, so that's it. Thank you and goodbye.